Hi everyone, we are from Group 5 and we will be talking about the Teluk Aman oil and gas field. I will start with a brief introduction of the Teluk Aman Field. The Teluk Aman Field is located about 60 kilometers offshore Terengganu in Peninsula Malaysia. This field is considered a shallow water field with a water depth of approximately 180 feet, which is an important factor when we later discuss rig selection. In terms of geological setting, the field consists of interbedded sandstone and shale sequences which were deposited in a shallow marine depositional environment. This type of formation is commonly associated with good hydrocarbon potential, especially in offshore Malaysia. The reservoir age for Teluk Aman Field is Middle Miocene, which is a productive interval in this region. The reservoir contains light oil with associated gas, which is favorable for production. From a safety and processing perspective, the reservoir has no H2S, which reduces corrosion and health risks, and the CO2 content is less than 3%, meaning gas treatment requirements are relatively minimal. Based on the field conditions, the jackup rig is selected for drilling operations at the Teluk Aman Field. The jackup rig is specifically designed for shallow water operations, and it is suitable for water depths of up to around 180 meters, which comfortably cover the field's water depth. In terms of design, the jackup rig consists of three main components. First is the hull, which provides buoyancy and supports the drilling and living facilities. Second are the legs, which are lowered to the seabed and support the entire rig structure. Third are the spike cans, which are attached at the bottom of the lake and help distribute the load while anchoring the rig securely to the seabed. There are several advantages of using a jackup rig for this field. It provides a very stable drilling platform, which improves drilling accuracy. It is cost-effective compared to floating rigs, especially for shallow water operations. The design is simple, making operation and maintenance easier. Additionally, jackup rigs have a high load carrying capacity and can be relocated and reused, which adds to their economic efficiency. Most importantly, because the rig is firmly fixed to the seabed, there is minimal movement during drilling, which enhances safety and operational performance.
Next, I will explain our directional drilling design for wells TA01, TA02, and TA03. Directional drilling was selected because the reservoir targets are laterally displaced from the surface location and therefore vertical wells are not suitable. The main objective in selecting the well trajectories was to ensure accurate target, minimize drilling risk, and maintain good wellbore stability throughout the drilling process. For well TA01, a J-type trajectory, also known as a build and hold profile, was selected. This well was drilled to a total depth of 8,400 feet with a kickoff point at 3,200 feet, which was obtained from the casing setting depth craft under surface casing shoe. A build-up rate of 2 degrees per 100 feet was applied. This relatively low build-up rate was chosen to minimize dog-leg severity, which helps to reduce torque and drag during drilling. A smoother wellbore curvature also facilitates casing running and cementing operation while reducing the risk of wellbore instability. Similarly to well TA02, also use a J-type trajectory, but it is drilled to a deeper total depth of 10,000 feet. The kickoff point for this well is at 3,400 feet, located below the surface casing shoe. For deeper wells, maintaining a controlled and smooth trajectory is very important to prevent excessive mechanical stress, friction, and cumulative torque along the wellbore. Therefore, using a J-type trajectory with a moderate build-up rate allows the well to reach the target efficiently while maintaining drilling safety and operational simplicity. Overall, the use of J-type trajectories for TA01 and TA02 aligns with recommended drilling practices where simple two-dimensional trajectories and low to medium inclination angles are preferred to minimize drilling complications and facilitate logging and completion activities. Finally, well TA03 was designed using a S-type trajectory, which consists of 3 sections which are build, hold, and drop section. This well was drilled to a total depth of 9,800 feet with a kickoff point at 3,400 feet. The build-up rate was set at 2 degrees per 100 feet, followed by a lower drop-off rate of 1.5 degrees per 100 feet. The S-type trajectory was selected because TA03 is a water injection well. Water injection wells require a near vertical or low inclination entry into the reservoir to ensure uniform water distribution, good injectivity, and effective sweep efficiency. By incorporating a controlled drop section, the well inclination can be gradually reduced before reaching the injection zone while keeping the lead severity within acceptable limits. In summary, the directional drilling design for all 3 wells carefully balanced mechanical limitation, drilling safety, and reservoir requirements. G-type trajectories were selected for production wells to ensure simplicity and stability, while the S-type trajectory was chosen for the injection well to meet specific reservoir performance objectives. Firstly, this spider plot shows the horizontal displacement of our 3 production wells from the surface location to their respective target reservoir. The main purpose of the spider plot is to ensure accurate well placement, proper well spacing, and to avoid well collision, especially in offshore multi-well drilling. From the table and spider plot shown in report and Excel, TA01 is drilled to a total depth of 8,400 feet with a displacement of 1,200 feet north and 800 feet east targeting reservoir X. TA02 reached 10,000 feet, displaced 1,500 feet south and 600 feet east targeting reservoir Y, and TA03 is drilled to a 9,800 feet with 700 feet north and 1,000 feet west displacement, also targeting reservoir Y. This spider plot confirms that all wells reach their intended targets without overlapping path. This layout improves reservoir drainage efficiency while maintaining a safe distance between wells, which is crucial for drilling safety and long-term production performance.
Next, I will discuss the casing setting depth and casing size selection, which were determined using the optimized skid tolerance method based on formation pressure profiles. Skid tolerance represents the maximum volume of formation fluid that can enter the wellbore without exceeding the fracture pressure at the previous casing shoe. Therefore, casing strings are set at depth that provide sufficient well control margin during drilling. From the casing setting depth graph, casing seats are selected at depth where the safe drilling window narrows, indicated by the convergence of pore pressure and fracture pressure. Displacement ensures adequate skid tolerance while maintaining safe mud weight limits. The same casing size are applied for all 3 wells to standardize the drilling design and simplify operations. These sizes include an 18.625-inch conductor casing, 11.75-inch surface casing, and 9.625-inch intermediate casing, and also a 7.625-inch production casing. The selected casing size and setting depth ensures effective formation isolation, sufficient skid tolerance, and safe pressure control throughout drilling, while minimizing risks such as low circulation and wellbore instability. In casing design, weight calculations are essential to ensure that the casing can maintain mechanical integrity throughout drilling and production operations. During drilling, casing is exposed to pressure and mechanical loads, and if these loads are not properly considered, casing failure may occur. The 3 most important casing failure modes are collapse, burst, and tensile failure, and these loads govern the selection of casing grade and weight. First, collapse load occur when the external pressure acting on the casing greater than the internal pressure support from the fluid inside the casing. This condition is critical during cementing operations, low circulation event, or when the casing is partially evacuated. For the Teluk Aman Field, collapse load evaluation considers external pressure from formation pore pressure and cement slurry, while internal pressure is assumed to be the minimum hydrostatic pressure of the drilling fluid. In practice, collapse failure tends to be sudden and occurs with little warning, which is why conservative assumptions are applied. Therefore, a collapse safety factor of 1.0 is considered acceptable when worst-case external pressure are already assumed. Next, burst load occurs when the internal pressure inside the casing exceeds the external pressure support. This situation is most critical during well control event, pressure testing, or gas influx. Burst loading is closely related to operational conditions, as internal pressure can increase rapidly due to kicks or pressure tests. For this well, burst load evaluation is performed by considering the maximum anticipated internal pressure, while the external pressure is provided by the drilling fluid column. A burst safety of 1.1 is applied to account for uncertainties in pressure estimations and operations. The same casing grades selected for collapse are remain for burst resistance, confirming that the casing can safely contain internal pressure without failure. Finally, tensile load refers to axial forces acting on the casing, mainly caused by the self weight of the casing string during installation. Additional tensile loads may result from cement weight, overpull, shock loading, and pressure testing. Tensile failure is largely a mechanical handling issue, especially in offshore operations, where hook load limits and running conditions must be considered. For this well, tensile load evaluation focuses on casing running, cementing, and pressure testing, with the maximum tensile load assumed to occur during casing installation. A tensile safety of 1.8 is applied, and the selected casing grade are confirmed to have sufficient tensile strength to withstand all these expected loads. In conclusion, by evaluating collapse, burst, and tensile loads with appropriate safety factor, the casing design for the Teluk Aman Field is confirmed to be safe, fit for purpose, and operationally reliable, while also avoiding unnecessary over-design.
Okay, so let me begin with section 5.0, which is the drilling fluid program. The drilling fluid is used in Teluk Aman Field is water-based mud, specifically a KCl polymer mud system, which also known as a potassium chloride mud. So this type of a drilling fluid is commonly used because it is effective in inhibiting shale swelling, maintaining wellbore stability, and providing suitable rheology and filtration properties during the drilling operations. Further details regarding selecting the KCl polymer mud system will be discussed in the next two sections. Okay, so next I will move on to the next section, which is casing cementation program. As we know that cementation is a process of preparing a cement slurry by mixing cement with water and pumping it down through the casing and into the annulus, which is the space between the casing and a three-well bore. So, for the Teluk Aman Field, Class 3 and Class D cement are selected. The depth for each casing setting are summarized in the cement program table for well TE01, TE02, and TE03. So, Class G cement is selected because it can be used up to a depth of 8,000 feet. It's highly versatile and can be modified with additive to suit different well conditions. It is also the most commonly used cement in the oil and gas industry. On the other hand, Class D cement is selected for a deeper section because it is suitable for a depth between 6,000 and 10,000 feet and perform well under moderate high temperature and pressure conditions. So, and in addition to cement class selection, cement additive play an important role in controlling its slurry properties such as density, setting time, and durability. For the oil producer well, Halliburton retarded HR5 is selected as an additive. HR5 is added at approximately 0.2% per 94 pound per sack of cement. This retardant slows down the cement setting time at the bottom hole temperature of 260 degrees Fahrenheit, allowing sufficient time for proper cement placement and reducing the risk of premature setting. In contrast, for the well injector well, which is the A03, LA2 latex is selected as the cement additive. Water injectors are continuously exposed to water, which can weaken cement over time and increase the risk of casing corrosions. So the addition of LA2 latex improves the cement flexibility, reduce permeability, and enhance a long-term durability under continuous water exposure. So in the conclusion, the correct selection of a cement class and additive is essential to prevent fluid migration, maintaining zonal isolation, and ensure overall well integrity and safety. When the cementing program is completed, a well fit chart is used to provide a clear overview of a well structure and the casing arrangement for the Teluk Aman Field. So, in this field, there are three wells with two different objectives. So, well TA01 and TA02 are an oil producer, while the TA03 is a water injector. All well follows a 4-string casing program consisting an 18 5/8-inch conductor casing, 11 3/4-inch surface casing, 9 5/8-inch intermediate casing, and 7 5/8-inch production casing. Although the casing design is similar, their functional and operational will differ significantly. The oil producers are associated with a higher operational and completion risk due to the hydrocarbon flow, pressure fluctuation, sand production, and a complex completion system. So in comparison, the water injector has a simpler downhole equipment and lower operational complexity. However, it relies heavily on a high-quality cementing and effective zonal isolation to prevent the unwanted fluid migrations. From an economic perspective, oil producers involve a high capital and operating expenditure, but failure results in immediate production loss. Water injector, although lower in completion costs, provide indirect economic benefits by maintaining a reservoir pressure and improve the hydrocarbon recovery. Therefore, both well types play a critical role but different in an overall field development.
The potassium drilling hazards
First, shallow gas hazard. Shallow gas may exist in unconsolidated seabed formations. If encountered, it can expand rapidly, causing seabed cratering and potential loss of well control. Risk is reduced by earlier surface casing installation and pilot hole drilling to detect gas zones before full drilling. Second, weather instability in shells. Reactive shells can become unstable when exposed to water-based mud. Fluid invasion causes clay swelling, pore pressure increase, and strength reduction, which may lead to borehole collapse and washouts. Third, shell instability mitigation. KCl polymer inhibitive mud is used to reduce shell hydration and swelling. This improves hull stability, reduces torque and drag, supports smoother casing running, and limits time-dependent shell weakening. Fourth, differential sticking occurs when drill pipe sticks against permeable formation due to high overbalance and thick mud cake. Prevention includes optimizing mud weight and minimizing open hole exposure time. Fifth, kick and well control risk. In narrow pressure window, mud losses can reduce hydrostatic pressure and allow formation fluids in, causing a kick. Control relies on proper casing depth, pit monitoring, flow checks, and strict well control procedures. 6. Low circulation happens when mud pressure exceeds fracture gradient and fluid is lost to the formation. Managed through careful mud weight control, LCM, and earlier casing to protect weak zone. 7. Shell dispersion. Clay-rich shell in upper section may break into fine particles when exposed to water-based mud, weakening formation integrity. This process is time-dependent, meaning the longer the shell is exposed, the worse the dispersion becomes. Using inhibitive KCl polymer mud system and minimizing shell exposure time are key methods to control this issue and maintain good hull conditions. Last, corrosion risk. Finally, small amounts of carbon dioxide in the formation can create an acidic environment which may corrode the casing. To minimize the risk, corrosion inhibitors are added to the system and suitable casing materials are selected to ensure long-term well integrity. This slide summarizes the cost and schedule comparison for 3 appraisal wells, TA01, TA02, and TA03. The well range in depth from about 2,560 to 3,048 meters RKB with a total campaign duration of 175 days. TA01 required 53 days while TA02 and TA03 took 16 and 62 days respectively, with completion time fixed at 15 days for all wells to reduce uncertainty. The original cost estimates were prepared in Malaysian ringgit and converted to US dollars using a January 2026 exchange rate of 1 ringgit to 0.253 USD for benchmarking purposes. TA01 is the most efficient well at approximately 26.2 million USD, while TA02 and TA03 cost about 31.1 and 30.5 million USD, mainly due to increased depth and longer drilling time. TA01 has the lowest total well AFE at about 103 million ringgit, mainly due to its shallower depth and shorter time compared to the other wells. TA02 records the higher cost at approximately 123 million ringgit, which is driven by its greater depth, longer drilling duration, and increased use of rig and service-related resources. TA03 has a slightly lower cost than TA02 at about 120 million ringgit, reflecting its marginally shallower depth and reduced operational exposure. Overall, drilling costs dominate the total AFE, particularly contract services and rig expenses, and the variation in well costs is primarily controlled by well depth and drilling time. These AFEs provide a realistic and justifiable cost estimate for offshore drilling operations. This slide discusses a proposed future technology to address wellbore instability in eruptive shell formation. Wellbore instability is a common drilling hazard in shell because during drilling, the original in situ stresses around the formation are redistributed. At the same time, drilling fluids invade the shell. This fluid invasion causes shell hydration and swelling, which increases local pore pressure and weakens the formation. If not controlled, this can eventually lead to borehole enlargement or collapse. To overcome this problem, an adaptive shell responsive drilling fluid system is proposed. In this concept, a stabilizing agent is premixed with the drilling fluid at the surface. During normal and stable drilling conditions, this agent remains inactive and behaves like a conventional drilling fluid. The key idea lies in how the system responds only when instability begins, when the drilling fluids enter a reactive shell zone and earlier weakening occurs. such as the formation of microfractures or increased field stress invasion. These local changes trigger the activation of the agent. Importantly, this activation happens only near the borehole wall and in the near wellbore region. Once activated, the stabilizing agents form a thin temporary low permeability layer. As a result, shell hydration and swelling are reduced. The localized pore pressure increase is controlled and the effective stress around the wellbore is maintained. This significantly lowers the risk of progressive wellbore collapse without the need to increase mud weight or reduce the pore pressure fracture gradient window. From an operational perspective, the system offers clear advantages.